All had your break? This last lecture and this lecture? All ready? Okay. So, how long has the winter school been going on? 5 days. So you all tired, excited? What's happening? Both. Very good. It's a good sign. And have you had the visit to GMRT so far? So it's going? Okay, good. Alright, good. So this will help you be a bit more prepared. Sunday, is it? Staying overnight? No. Going in the morning, coming back in the evening. Alright, good. Okay, so what kind of lectures you had on radio astronomy so far? Different fields of yes. Okay. And in terms of actual techniques, have you had any lectures? Interferometry? No.
Just an introduction.
Introduction. Okay. And what did you learn in that introduction?
The techniques of the radio astronomy.
Okay. Right. So if I ask you what is Jansky, what will you say?
The brightness measurement of list for radio astronomy.
Good. And what are the units of Jansky?
10 power minus 26.
Right. You guys are good. All right. Good. Okay. So we will. What we will do is we'll talk our way through some more detailed concepts of radio astronomy. And taking the GMRT as an example of what is happening, and looking further ahead to the what is called the square kilometer wave, SKA. Any of you, obviously you've heard about GMRT, right? Otherwise I'm going to ask you to leave the room. Okay, what about SKA? You heard about it? Okay, who's going to tell me what is SKA? Very quickly, in one sentence.
Kilometer array of radio.
What does that mean?
We have a area of 1 square kilometer where array of radio telescopes are.
Area of 1 square kilometer. Okay, well, when you go to GMRT, you will see the GMRT is already covering 1 square kilometer in terms of area. So it's not really the area of over which the antennas are spread out. What else can it be?
So basically the tiles that have those spiders in which collect data and
yes.
just process this have
Reading from somewhere. Alright. Okay. Yeah.
Maximum baseline is.
So it's not the maximum baseline. So it's really the total amount of physical area over which the signal is being collected in terms of the area that the dishes or the tiles would cover. They may be spread out over any distance, but the actual amount of collecting area that they represent, that is 1 square kilometer, which is huge. So it's like saying that it's an antenna whose area is 1 kilometer by 1 kilometer. Okay, of course it's not in one piece, and that's what we will see. Okay, all right. So so this part I should not have to talk much to you all, right? And that the fact that we can do astronomy at different wavelengths is something that you all are well aware of. What is the range of those wavelengths? I hope you're all well aware of, going all the way from the lowest frequencies, which are the radio waves, which is the largest wavelengths, up to the highest frequencies, which are the gamma rays, and the shortest wavelengths, right, spanning the entire electromagnetic spectrum. And that the fact that objects in the universe can and do emit at all of these range of frequencies is something that was realized relatively late, after many decades, if not centuries, of just optical astronomy. But people did realize that this can happen, and of course, in order to do this, it's not enough to know that this can happen. You need to be able to receive those signals, right? So we have the natural receptors, which are our eyes, which are sensitive only to optical, right? So you need the corresponding detectors to detect the signal at any wavelength in order to study any object which is emitting that wavelength. So those detectors came for radio astronomy from the development of communication technology. So when man learned to generate electromagnetic waves, so who's the first person who produced electromagnetic waves? Hertz. If you are a proud Indian, you will say J.C. Bose, right? Okay, so that controversy exists, right? But never mind all that. So people learn how to generate electromagnetic waves, and then you learn how to receive them, right? And this, to receive it, you need to build the equipment which can detect that signal and show you the result from that. And that's what is a basic detector. And that came as an offshoot of this radio communication technology. And in particular, what happened was, I thought I have that here, but never mind. So in particular, what happened was that when they built the first transatlantic communication equipment to send radio waves from North America to Europe, they found that that equipment was giving trouble. There was lots of unwanted hiss and noise coming in the equipment, which was not expected from the way it was designed, and was affecting the quality of the transmission. And so the engineer named Carl Giamatti in Bell Labs was given the task to debug and find out what's wrong with the equipment. And to cut a long story short, he built a basic antenna which could then try to understand where this unwanted signal was coming from. And he did a series of experiments which showed that this was not coming from any terrestrial source of noise, which is what people were expecting, but was coming from somewhere in the galaxy far off. And that's how the whole study started. So that with that detector and with the first understanding that you can pick up signals, we have moved a long way in terms of having modern radio telescopes. Now, in principle, the radio telescope is no different from your favorite satellite dish, without which you can't live, right? And so what it does, it collects radio waves coming from a distance. In the case of satellite dish, they're coming from the satellite in orbit around the Earth, and they bring the signal to a focus, either at the primary focus here, or in some cases the secondary focus, where the signal is further reflected. But finally, you pick up that signal in the sense that you convert the electromagnetic wave into a voltage, right, with a particular device which has the property. Again, as part of this detector technology that we were talking about. And then you basically want to study that signal, and you would then amplify it, detect it, convert it into an intensity, and then study the strength of that signal as a function of looking at different directions in the sky to detect different sources, and then study the various detailed properties, right? So you say, well, that sounds very simple. We can do this easily. The problem comes when you realize that, as you yourself told me a few minutes ago, that 1 Jansky is 10 to the minus 26 watts per square meter per hertz, and you say, well, it's just a number. The number makes sense if you try to convert that if I were 1,000 square meters of collecting area, how many watts am I getting, and over what frequency I'm observing. Let's say I'm observing over 1 megahertz of bandwidth, then how much signal you're getting. You do all that and you find that the signal is very, very, very weak. Okay, and there are various ways of looking at it. If you understand electrical engineering, that's minus 100 dBm, which is compared to 1 milliwatt of power, that much weaker. Or there are other ways of more interesting ways of looking at it. So the point there is that you can't quite treat it like your basic satellite dish. And so you say, all right, what does it mean? It means that you need a large enough collecting area to be able to collect enough of that signal that you can detect it easily. So you would ask, what prevents you from detecting that signal if it is a weak signal? So the problem comes that any system that you have where you pick up a signal, amplify it, detect it, has its own noise. Okay, the noise comes from the electronics itself. So I don't know how much of electronics you all know, but any electronics device has intrinsic noise of its own, which is a random fluctuation of fluctuating signal, which can interfere. So just like if I'm trying to talk to you and there's lots of noise of other people randomly talking in the room, you will have difficulty in hearing me. So in the same way, if there is random noise introduced in the system, the actual signal that you are trying to see can get masked or hidden or buried under the noise. And that is the major challenge, that the noise is unavoidable. You can try to reduce it. You can ask the others to shut up and then the noise will come down. In the same way, you can try to build electronics which produces less noise, but you can't make it quite zero. It will always be some amount of noise. You can try to be clever and try to reduce it to as much as possible. The more you reduce it, as you can see, the fainter signals you can pick up with the same antenna. Okay? So basically what happens is that you have to build a very large antenna so that you can collect enough signal, and you have to build as good quality electronics as possible to minimize the noise and the unwanted signal that comes. And furthermore, in order to further improve the signal to noise, that is the main criteria, that how strong is the signal and how much is the noise. That is what decides whether you can see a weak source with your radio telescope. And so in order to improve that, you try to observe over as large a bandwidth as possible. So this per hertz, if you can observe over a larger amount of per hertz, then you will get a larger amount of power coming. And since most of the natural phenomena that we look at are all generally broadband phenomena, unlike man-made transmissions where you transmit over a limited frequency because you're transmitting some coded information on a carrier, most of these are natural broadband phenomena. Just like sun emits light, it emits light over a whole range of frequencies. In the same way, the phenomena in the radio regime also will typically, the object will emit over a large range of frequencies, hundreds of megahertz, except for spectral lines. You know what are spectral lines? You studied that, right? So that is when you get radiation due to specific transitions of atomic and molecular states. That by nature is a narrow frequency of radiation. It is not over a large range of frequencies. But most of the other kinds of radiations are all broadband. So you can take advantage of that by observing over as large a bandwidth as you can build the antenna and the receiver and the detector to be able to support. Okay? And further, because most of the sources that we observe are on pretty much forever as far as human lifetimes are concerned, you can observe the source over a long duration and integrate the signal. Okay? So if you integrate a signal, you tend to reduce the effect of noise, because when you keep integrating, noise adds randomly. So its strength does not grow in the same manner as the strength of the signal grows when you integrate. Okay. Again, I don't know whether you've come across these concepts in any of the other talks or lectures, but basically the more bandwidth of observation you use and the longer you observe the source, the better signal to noise you can get with the same instrument, same antenna and the same detector. Okay, so these are the basic driving forces which drive what kind of radio telescopes you build, right? You try to build as big an instrument as possible with as low noise electronics and as large a bandwidth as possible, and observe as long as possible. Now, there is one other thing that remains in this, that obviously the sensitivity depends upon the size of the antenna, right? The bigger you make it, more sensitive it is. But there is other concept which is resolution. Have you come across this concept? What is the meaning of resolution?
Separate the two base sources.
Yes. So the resolution means how well, how easily can you separate two sources which are very close by in the sky. So what that means is that your instrument should have the angular resolution capability, which means that it should be sensitive to the direction from which the radiation is coming. So if you move it slightly, then only will it see the other object. Otherwise, it will not see. Or when you make the image, you should be able to clearly see the two objects. Now, in all cases, the resolution depends on the aperture or the size of the instrument and the wavelength. This you would have also studied. It comes from the basic diffraction theory, that if you have radiation at wavelength lambda being observed with an aperture of size d, then the resolution of that instrument is of the order of lambda by d. Okay, and so if you do this exercise for radio wavelengths, so let's take a typical radio wavelength of 1 meter, which is 300 megahertz frequency, and you take an antenna of 100 meters, which is a huge antenna, and you ask what is the resolution, you do this, it comes out to be half a degree. Now what is half a degree? You need any object whose angular size is half a degree? Moon and the sun, right? So what does this mean? That means if you use this antenna and look at any area in the sky, any finer detail, finer than the size of the diameter of the sun and the moon, will not be visible to you. It will be a blurred object of that size. Okay, so that's a very poor resolution. Even with the simplest optical telescope, where the lambda is much smaller, you can see the details on the moon, right? With your own simple toy telescope or binoculars, you can do that. So it clearly says that you have a big disadvantage working in radio frequencies, right? And I guess you all heard how radio astronomers worked around this disadvantage and what was done to overcome this problem, right? And that is what is interferometry, which you have said you've had some exposure to. And what interferometry allows you to do is to say, well, sorry, I can't build an antenna which is few kilometers in size. It's unaffordable. I cannot manage to build such a structure and move it around and point in different directions. But what I can do is build smaller antennas and cover that area that I would have liked to build a large antenna. And combine the signals coming from all of these antennas in a clever manner so that I can then synthesize an equivalent signal which I would have got if I had an antenna whose size was equal to this largest separation, which you people were telling me earlier, baseline and so on, right? And but mind you, this is only as far as the resolution is concerned, right? So it will give you the resolution which is comparable to the resolution of an aperture whose size is ds, where ds is the largest separation between the antenna. Of course, it will not give you the sensitivity of an aperture of this size because large areas of this aperture are empty, right? You have only, you're picking up signal only in these places, right? But resolution wise, it will give you a resolution which is comparable to an antenna whose, single antenna whose size was ds. Okay, so with this background, we will move on and ask how such interferometry or aperture antennas are built and how they are used for doing radio astronomy. And we will start with our own GMRT, which I was telling you earlier, we are working in the lower frequency part of this radio spectrum. So the radio window, which I showed in the earlier graph, goes all the way from something like 30 megahertz to 300 gigahertz. It's a huge range in frequency or wavelength. And no single radio telescope can really cover that entire range because, again, you can't build a detector which will work equally well over the entire range of frequencies. And so often the radio telescopes are built to specialize in some part of that spectrum. And so we specialize in the low frequency part from around 50 to 14, 15 megahertz. And this is something that was being built in the late 80s and been operational since 2001. And as we were discussing earlier, 30 antennas, each of 45 meters in diameter, and arranged in a roughly Y-shaped structure with a central 1 square kilometer, not to be confused by the square kilometer array as we talked about, having about 12 antennas and the remaining 18 spread out like this. And again, so it allows you to synthesize a telescope whose diameter is 28 kilometers or so and get resolution which is corresponding to that. And the older GMRT system, and I'll tell you what we are doing for the upgrading it to improve its performance, works in these 5 discrete frequency bands with a maximum instantaneous bandwidth of 32 megahertz. So this is that per hertz business that we were talking about. So we can observe over a contiguous band of 32 megahertz at any one of these frequencies. Okay, and this is this collecting area, that is the total area of all the antennas put together, right, 30 antennas. And we talked about this interferometry or aperture synthesis mode, which is the main motivation to spread out the antennas over a large distance. But you said you've heard about pulsars and things like that, right? So one of the things you would have understood from pulsars is that pulsars are very compact, they're very small, and the region of radio emission is a very compact region. It is so small that even with this resolution, you cannot make out the details. So there are objects like that which are so compact that even with these large baselines, you cannot get resolution enough to see the details. They'll still look like a point, okay, in your image. Whereas some of these objects, especially pulsars, have this interesting property which goes against my first statement that objects are continuously on all the time and emitting, so you can integrate the signal over long duration. These are objects where the signal fluctuates, it goes on, off, like pulses. Okay, so you can't apply that same criteria of integrating over long duration, because then you will wash away the pulses and you won't see the pulses. Whereas the whole idea is to see the detailed structure of the pulses and try to understand what is the nature of the emission, what we can learn, and so on. So for those, there is a different mode of operation where you say, look, I'm not interested in this combining these signals in a clever manner and for each baseline and making an image. I just want to collect all the signal together, because you're giving me 30 places where I can collect the signal. I just want to add it in simple adding machine so that I get the maximum signal to noise from the instrument. Okay. So that is what we call the array mode, where you don't do the complicated signal processing that is required for the interferometry, but you simply add the signals from all the antennas to maximize the amount of signal you can collect, and you don't worry about the resolution. That the resolution be the same as the resolution of the single dish, you are not interested in that. Okay, and so both these modes are supported, which allows you to study the different kinds of objects. Okay, and so I'll just show you some pictures. You will see it from the ground, but you can see it also from the Google satellites. And so this is the central 1 kilometer by 1 kilometer area, and you can see individual bright spots which are the antennas, and you can zoom in. And so you can see now the antennas are at different locations, different distances, again to give you different baselines, short baselines, long baselines, and so on. And so these are three of the closest antennas. The signals from all the antennas is brought to the central receiver room, which you may get a chance to visit when you are there over the weekend. And that is where the final signal processing is done. There's a certain amount of processing done at the antenna itself, in terms of the initial amplification with the low noise amplifiers, and then the modulation onto the optical fiber, and then demodulating it here and doing the rest of the processing. And there's in this corner is the control room, which again you may get a chance to visit when you're there, where you can run and control the entire observatory and monitor what's happening, including the data that's being recorded and so on. Right, and so just some. So if you, I guess if you're staying only for a day, you won't get a chance, but you should go climb the nearby Narayangarh hill. And if you do, then you'll get views like this of the array. That depends on how much time you have there, but you can go again later on sometime. Okay, so this is a close-by view of the antenna, and it tells you how big it is. And like I was telling you in the beginning, that the signal can be brought to focus either at the prime focus of the dish or at secondary focus. So we have a prime focus instrument, and so right at the top over there, at the apex, there are these elements which can pick up the electromagnetic waves and convert them into a voltage, which is then amplified. So there is electronics sitting right there in boxes, which amplifies the signal, does the initial signal conditioning, and the signal is sent down on cables to the bottom of the tower, where there is more electronics, and then it is put onto the fiber in central building. And so you have to access this in order to put electronics there, maintenance and work. So this is a kind of a crane, special purpose crane, which goes up to 32 meters height to reach the antenna. But one of the striking things you notice, if you see this and you say, well, how can this be an antenna? Because it looks like completely transparent. How does it reflect the waves? Right? Unlike your satellite dish, which is a solid surface. So this also has a surface. It's not solid. It is a wire mesh which is built there. So who can explain why you need a wire mesh here and why you need solid in your satellite dishes?
So because the radio is very large, so
yes,
even small gaps, they will not really create much problem. So, I mean, you can get that resolution here by.
So how small can the gap be, or how?
Smaller than the length or wavelength you're of.
Yeah. How much?
Should be smaller than 20.
Compared to the
Yes.
what wavelength you're observing.
Yeah. So the mesh size should be at least lambda by 10 or smaller, where lambda is the smallest wavelength you want to operate, which in our case happens to be 21 centimeters. So our mesh has dimensions which are of the order of few mm by few mm up to 10 mm by 10 mm and so on. Okay. And so you can wonder why it's a mesh and why not solid, but that's, we can talk about it separately. And so, but in order to make something like this work, as you can probably begin to feel by now, that there's a lot of different subsystems that need to be designed and be in place to make the whole thing work. And it ranges all the way from mechanical itself. I mean, making an antenna like this, mechanical structure is a challenge. And then, as you will know, that you have to move this in order to follow objects as the Earth rotates. And that's a very precision movement. You have to be accurately know where you're pointing and be able to keep that pointing as you track objects in the sky. So there's a system designed for doing all of that. And then finally, when you pick up the signal, that is what we call the feeds, these things over there. These are very crucial because these are the ones who actually convert that electromagnetic energy into voltage. And this is the one that decides what range of frequencies you can really pick up in one go, and so on. And again, not one of these can cover the entire frequency range of interest. So those 5 discrete bands that I talked about, they are all achieved by these combination of these feeds. So this particular feed will work at one of those frequencies, the one that's pointing upwards will work another one, and so on. And depending on which frequency you want to operate, you will rotate. So this thing is actually a rotating turret. You can rotate this and bring the desired feed to the focus to point the dish. So it will pick up the radiation at that frequency, and it will not work at the other frequencies at that time. And then you rotate it for working to different frequencies. So that is this position and control of the antenna feeds. And then once you pick up that voltage, as we said, it's a very weak signal. It needs a lot of amplification with the good quality electronics. And so there is this whole receiver chain which has all kinds of electronics, starting with the most crucial one up there, and then some more over here, and then some more in the central receiver room. And then the whole optical fiber system, which allows this transport to happen. Optical fiber system also allows you the monitor and control. So when I said that you can sit in the control room and do everything, it then has a complete chain of commands whereby it can talk to each antenna, to every subsystem of the antenna, whether it is to move the antenna, to track something, or to select the frequency, to set the settings in the electronics. All of that can be done by the monitor control system, which again uses the optical fiber as the media for talking to the antennas and to all the electronics of the observatory. And then finally, when the signal comes, you digitize it, and then the rest of the processing is done in the digital signal processing domain. And this is what I already talked about, the telemetry subsystem, which allows you to monitor control. And then a lot of software at the level of running it as an observatory, because you have to do a coordinated series of operations to do a whole sequence which makes an observation. And that requires a full-fledged software for doing that. And then there is the software and the algorithms for the actual offline processing of the data. Once you get the data, what do you do with it? How do you make the image? Or how do you study the pulsar signal? All of that requires a lot of additional signal processing software before you can get the final quantity of interest from which you can do the science and understand the physics of the objects. So as you can see, there's a complicated chain of engineering and technology which goes into any of these instruments. And what I'll do is I'll just briefly talk through some of this. So you can break it into these very basic blocks. The feeds which pick up the signal, the front-end electronics, which is at the focus of the dish, then additional electronics at the base of the antenna, at which point you convert the RF signal into an intermediate frequency IF signal, which is transmitted over the optical fiber, transmitter, receiver, received at the central station, converted back into electrical signal, and digitized, and then processed in digital electronics. And so this is the main flow of the signal through the system. And there are lots of auxiliary things which are needed in order to make it happen for controlling and doing various conversions. I won't go into the details of all that. But finally you say, well, you've done all this, what do we get? So as a user, you are interested in the what we call the system level parameters of the observatory. Okay, what frequencies does it work at? What range of frequencies does it work at? When it works at those frequencies, what is the resolution I can get? What is the sensitivity I can get? How much noise do I still expect to come if I integrate for this duration? So that is what the user wants to know as an astronomer, because then they can plan their experiment based on the overall system parameters of the observatory. So here's an example of a system parameter chart for the legacy GMRT. Again, talking about those 5 bands in which we operate. Talking about the primary beam. So this is the resolution of the individual antenna. And again, as you can see, as you change the wavelength, the resolution changes as lambda by d. Okay, and then this is the resolution that you get when you finally synthesize and make the image. Then now you can see from degrees you've gone to arcseconds in terms of the resolution, and that is this effect of having the antenna spread out over a large distance. And this is the effective area that you get from all the 30 antennas. So each antenna is about 1,000 square meters of collecting area. It is a bit less at higher frequencies. I leave that for you all to figure out what may be the possible reason. And this is the quantity that tells you how much is the noise that the system has. Like I said, you can reduce it, but you cannot eliminate it. And part of the noise also comes from the sky background. We didn't talk about it, we only blamed the electronics, but you get noise from the sky itself. You know where that comes from? What is it due to? Well, yes, but even beyond, not responsibility of man, or not it comes from. Yeah. So there is a background. So one is the cosmic microwave background, but there is other background, which is the background of the galaxy itself. So the galaxy itself acts like a continuous, source of emission because of many objects in the galaxy, and that obviously changes. If you look in the galactic plane, you will find a higher background. As you move away from the galactic plane, you look away perpendicular to the galaxy, you find less galactic background. But that is all noise coming from the galaxy. So all of that contributes and gives you a certain, and it's measured in the effective temperature as a noise temperature. And then finally it tells you that this is the kind of noise. So you see our Jansky is back, but with a micro in front. Okay, so 10 to the minus 6 Janskys is, so you can make images where the residual noise will be of this order. Okay, by integrating the data for long enough duration and with careful signal processing of the data. So, okay, so as I was saying that this was built during the late 80s to the 90s and inaugurated in 2001 and has been operational since early 2002 for the worldwide user community and is used by people from all over the world. So this gives you an idea of the usage. So there's about 50% users from within the country and users from all other major countries in the world where radio astronomy is practiced. And it's typically oversubscribed by a factor of 2. When you say what does oversubscription mean? So the way the observatory works is that twice in a year, every 6 months, we put out a call for proposals. A call for proposals means anybody who has an idea that can propose an experiment, saying that, look, I would like to do this kind of science by observing this kind of source in this manner for this much duration, and this is the result I hope to get. So that's a proposal. The proposals are evaluated by an evaluation committee, which can call to any international expert for their opinion on the proposal. And finally, the committee then decides which proposals are good and how much time they should be given on the telescope. Okay, and so there is, now you can see there is a demand and there is a supply. So there is a limited amount of time you have in 6 months that you can make available for the observatory, and every 6 months there is a certain amount of demand. So as in any demand supply, there is a ratio, and we have a ratio where the demand is typically 2 to 2.5 times more than what the time available that we can supply. And so which means that there is a oversubscription. It is highly in demand. People want to use it, and therefore this process becomes really competitive. So only the best proposals where the science will have the highest impact or will make really difference get through and get time on the telescope. Okay, so you can ask, what do people do with that time? What kind of science is done? And this is just again a quick snapshot. We won't have time to go into the details. Some of the other talks, somewhere you will pick up about how GMRT can be used to study the sun, or to detect extrasolar planets, or to find young stellar objects, that is, young stars in the making, and so on. And then a lot of study of pulsars, which I myself work on. And again, you get to hear. And this should be galactic, different galactic objects like supernova remnants and so on, explosive events like gamma ray bursts, different forms of neutral ionized hydrogen gas clouds in our galaxy, nearby galaxies, faraway galaxies, and so on. Then studying radio galaxies at various distances in the universe, finding new radio galaxies, studying cosmology, the early universe, epoch of reionization, and various things. I don't know if some of these you would have had talks by now. Some of this you may get later on. So, and then things like all sky surveys. So, an all sky survey is a study where you study the entire sky as much as possible in a uniform fashion and make a complete map. It's like making an atlas. So you look at an atlas. Atlas has a uniform coverage showing you, an atlas may concentrate only on the natural things. It may show you only the rivers, mountains, and valleys and oceans. Or it may show you the countries and their populations and their capitals and so on. So, but it is a bit like an atlas where you survey the entire sky visible to you in a uniform manner at a given frequency and make like a series of maps which anybody can use as a reference, just like you use an atlas for a reference. So you want to go look up what does that country look like, you go open that page of the atlas and then you can see the details. And the same you want to say, what does that area of the sky look like at this frequency, then you can go look up the PGSS website and it will give you a set of images from which you can see what do I want to learn. If you want to say that I found an interesting optical object in that direction, what is the radio counterpart? Is there something in the sky? So you go look up the atlas and see what it is.
Sir, what is PGSS?
PGSS stands for TIFR GMRT Sky Survey. Okay, so it's like your favorite atlas will be Norton's Star Atlas, I hope, or something. So just like an atlas has a name, this has a name. Okay. So it was a sky survey done with the GMRT at 150 megahertz. Happens to be one of the most useful and successful sky surveys done at low frequencies. There is no corresponding survey at 150 megahertz. There are surveys at high frequencies, 1.4 gigahertz and so on. And it's very interesting. Now you can compare what the map looks like at high frequency and low frequency, and you can learn a lot about things happening in that area of the sky or in that patch of the universe. Okay, so with that small glimpse about the kind of science, we'll move on and talk about what we are doing now. So like I said, the GMRT has been operational for more than 15 years now, and quite some time back, almost 7-8 years ago, we realized that it's doing well, but what should we be doing, 10 years later? And that's when we took upon the idea of upgrading the GMRT. And the upgrade was started about 5-6 years ago with the following main targets. The main target was that instead of those 5 discrete bands of operation that I showed you, we would like to cover the continuously over the entire range of frequencies which our dish is sensitive to. So try to cover from, if possible, 50 megahertz to all the way to 1500 megahertz instead of those limited bands. So you can say, well, what's the problem in doing that? So you can see now the problem is those field elements at the focus. You have to come up with a new design which can really pick up large range of frequencies. Okay, and then the rest of the electronics has to be able to handle a much larger range of frequencies. So that's a major challenge in terms of design of completely new fields and receiver systems with large bandwidths. And while doing that, the aim was to improve the sensitivity. That means make it a little bit better, little bit less noise if possible, little bit more gain if possible, and so on. So that is measured by the ratio of the gain to the system temperature. Try to improve that with better technology of the receivers, and then try to increase this instantaneous bandwidth that you can use. So although you may be saying that I can receive signal anywhere from say 50 or 100 to 1500 megahertz, how much of it can you take in one go? So that is that bandwidth, which was 32 megahertz earlier, and the aim has been to increase it to 400 megahertz. You remember again from the very first slide that the larger the bandwidth over which you observe a source at a given time, more sensitive will be the observations. The whole idea is that you should be able to do much more sensitive observations if you can work over a much larger bandwidth. So these were the main goals driving the upgrade. Along with it, a few other things which you need. It's like if you run your car for 5 years, you'll say, well, I need new seats, or I need new paint, and all those various things without which it will fall apart no matter what you do to the engine. So, improved servo system to give it modern technology, improved motor control system with a modern software, and improved computing facilities, because now you're going to get much larger amount of data with much larger bandwidth and so on. So you need to be able to handle that. And improvements, you have to keep that exactly like the car. You have to keep your antennas working. If the mechanical system starts failing, corroding, rusting, then you won't have any antennas left. Similarly, electrical, you keep improving the system. So all of these are very infrastructure things. And one of the main challenges was that you should do this improvement without stopping the observation. It's like when your car goes for the improvement, you don't get the car for those days when it is in the workshop. Too bad. Okay, you have to find some other way of doing the things. So we didn't want that. We didn't want this observatory is shut down while the upgrade is happening, because the users can't use it anymore, and it's a big loss. And it's not small. So like your car can go away for a day or two, you're okay. If the car is gone for a week of repair, then you start becoming very uncomfortable, right? And if it's gone for a month, then you say, oh, gosh, I need a new car or something. So, and this upgrade we knew was going to last for a few years. So this was to be done that while it's going on, the observatory with its whole specifications, like the table that I showed, is still available to the user as far as possible. So you say, how can you do this? So what we did was that any improvement activity, upgrade that you do, you use the daytime during weekdays to put in, you change the receiver, you change the feed, whatever you're doing in each antenna one by one. In the evening, you release the whole system so that in the night it can still run as an observatory while providing the old specifications. So you say, well, you change something, made it new, how can it still work like the old? So that was the design challenge, that whatever new system you put in, it should at least give you, this is what is called backward compatibility, right? When you go to your new laptop and it says, my old thing is not working on the new laptop, what is this, right? So that fellow will support the old system while giving you new features and new capabilities, right? So this was our backward compatibility, that it should work for the old specifications and the old features so that users can use it. So night times, weekends, it is running like a normal observatory. Weekdays, daytime, it was taken over by the engineering team for doing the upgrade activities. So we were able to keep running the observatory. So total amount of time available, let's say that over subscription went up, because now we had less time available, because weekdays during the daytime we could not give the observatory for observations. Okay, so where do we expect the upgrade to take us? So this is a plot, is a measure of this sensitivity. So you see the same micro-Giamatti coming up that we saw. So it tells you that if you observe a source for 9 hours and do this aperture synthesis and make the image, then what will be the RMS noise in that image? Okay, and so it shows that on one axis and it shows the frequency on the other axis. So if you observe with the GMRT and today with the existing system at 150 megahertz, then this is essentially you get. If you observe at a high frequency, you get less. That you would see in that chart itself, because the noise is higher at the lower frequencies. So you get less sensitivity at lower frequencies, better sensitivity at higher frequencies. And it also shows with the purple circles that what will be the improvement in the sensitivity when you use the upgraded GMRT. So it tells you that now you will get an image with much less noise compared to the earlier image, if you use the new GMRT systems. And it also shows on the same graph the sensitivities of the other observatories around the world. Some which are just coming online, some which will be coming up in the future, and so on. So as you can see, finally, that most of these purple dots are at the same place or better than other dots from other observatories in the world. Like, so at this point we were worse off than LOFAR, but at this point we will become better than LOFAR. And here there's a new instrument, MeerKAT, in South Africa, which is just getting commissioned now, and we are already beating that in terms of sensitivity. And we are comparable in sensitivity to the very high frequency telescopes like the BLA, working at much higher frequencies than we work. So we stop over here at 1.4 gigahertz. And so you can ask, how can we be more sensitive when our noise is higher than their noise? But that is because, so I don't know if you've studied what is the spectra of a radio source, right? What is thermal spectrum, non-thermal spectrum? Have you studied that? So we look at typical radio galaxy. The strength of the radio galaxy will change with frequency. In what way is it expected to change? We look at a H2 region. In what way will its strength change with frequency? Have you come across these things yet? No? Okay, so basically what happens is, this shows the typical spectrum of a radio source due to the minus 0.7 as a, for a typical non-thermal radio source, like anything like radio galaxy, supernova remnants, and these kind of objects, where it is known by nature that the object becomes brighter at lower frequencies and is fainter at higher frequencies. So the guy working at high frequency anyway has a challenge. He has to make an image with less noise in order to see that same object, which I can see at low frequencies, by making an image which has higher noise, because the object itself is brighter. Okay, so you don't have to work that hard to see that object, and so that's why this is still matched. So as long as you are on this line compared to the high frequency telescope, you are producing an instrument which has a good capability. Okay, so this is how this was worked out. So basically you get an improvement in imaging and sensitivity and also pulsar observations. And of course, since you're opening a much larger part of the frequency spectrum now, you can see different spectral lines redshifted by different amounts. So are you comfortable with this concept, redshift of spectral lines? Everybody's nodding their head. Good. Alright. So what it says is that, and the most common spectral line is which one?
21 centimeters.
Yeah. So 21 centimeter neutral hydrogen line, which comes from the neutral hydrogen atom. And if you place it at further and further distances in the universe, then because of Hubble's law, where everything is in the expanding universe, everything is moving away from each other, the velocity of precession is higher the further away it is, and the line is redshifted to lower and lower frequencies. In fact, that was the motivation why the Giamatti was built, to cover that range of frequencies. That you can see redshifted neutral hydrogen from different parts of the universe by observing at different lower frequencies of Giamatti, right? And so those spectral lines will now get much wider access. You can sample the universe much more densely in redshift space to see objects at different distances in the universe at different times in the evolutionary history of the universe. Okay, so we'll just see a little bit about what is the new technology that has gone in doing all this, and then we will move on to the SKA. Okay, we are supposed to end at 12:45. Is that correct? One? Okay. This is the new receiver system, which in some sense is simplified from the old one, because we decided to remove much of the complexity of the antenna base. But it is much more sophisticated, because each of these elements which replace the old ones has much better capabilities in terms of the range of frequencies and the sensitivity of the amplifiers and the receivers and so on. What I'll show is just some sample. So the way it's done is, we still have this thing that you have only 4 faces on that rotating turret. So you can put only 4 feeds. It's not easy to put 5 or 6 feeds on that. And so we chose those 4 to cover this range of frequencies. Now you can see these ranges of frequencies are quite wide. They're almost like octave. Octave means the highest frequency is 2 times the lowest frequency. So like 130 to 260, 250 to 500 is almost an octave, 550 to 900. and then the highest frequency where it's difficult to do one full octave with 1000 to 1450 megahertz. And these replace the old systems which were working at a much narrower range of frequencies around 150, 325 and 60. So that is all, that change is all happening over here. And then you have to modify the optical fiber to carry this broadband signal. It was not designed originally to, it was only designed to carry this narrow 32 megahertz bandwidth signal. So this was redone with modern technology to drive the full bandwidth signal up to 2 megahertz if needed. And then finally you receive it. And then to get this 400 megahertz of bandwidth, there is a new backend system which can extract up to 400 megahertz of bandwidth. So, for example, full 1000 to 1450, this full thing can be processed, and this 250 can easily be processed, and so on. And then put it into digital systems which can do all these calculations which are needed either for the interferometry mode or for the array mode for getting the final data products. So, this is an example of the kind of engineering that goes into it. This is one of those new fields which works on 250 to 500 megahertz. This is the corresponding box which has the new low noise amplifier and the circuitry which goes with it. And this is this box at the top, at the focus, where this electronics sits, which takes in the signal from the field, amplifies it, filters it, and does various things and sends it down to the bottom of the dish. Okay, now this is a slightly old slide. So this is the status of what's happening. So we have finished this upgrade for all 30 antennas. In fact, as of last week, this is also finished for all 30 antennas. This also we finished a few months ago, and this is done now for 24 antennas as of last week, and will be finished soon. So, so all of these receiver systems are well in their way to completion to give the system for 30 antennas. And this is what will be the change in the frequency coverage of GMRT. So these narrow white rectangles show the current frequency coverage at those different bands that I was telling you. And the purple boxes show the new frequency coverage. So you can see there is much wider frequency coverage. There are small gaps where the places where the radio frequency interference is so strong that we can't work. And this is the one which keeps all of you happy with your mobiles. Okay? So this is when you talk on a mobile, this is where the signal sits, and we can't observe at that frequency because the mobile signals are so strong. These are some TV channel, terrestrial TV transmission. If you like the version, that is where it comes from, and so on. So, but other than that, we are able to cover a lot of the frequency space and try to do observations. Right? And this is just a view of the upgraded optical fiber system. There's a bit of technical details, so I won't go into all of that. And this is a block diagram of the backend system, which does this 400 megahertz processing. So this uses a combination of technologies, high-speed A to D converters, FPGA circuits, and GPUs. It's like a small supercomputer connected with an InfiniBand switch to do all this high-speed digital calculations to give you this 400 megahertz bandwidth correlated and freeform and pulsar receiver system. Right? And okay, these are the, if you are interested in technology, then there's lots of high tech and some of the things that go into doing all this. And this is also now all done and available for the full 30 antenna system since almost close to a year now. And so basically now the first few science results have started to come from the updated system in the last year or so already. And so I just show you. So whenever you build a new system, you do the initial tests, what is called commissioning. That is, it working properly as per the expectations, as per the design. So these are like test observations. Okay, you will go look at a known source. I know what the source should look like, and if I observe for this long, I should see this much noise in the image. Am I seeing this? So those are the kind of tests. And the way we designed the system, like I said, since we wanted the whole system to be available and working all the time, the whole electronics was designed that both the receiver chains are working simultaneously. So you can get data from the narrow 32 megahertz system, and you can also get data from correspondingly from the full wideband system. And you can record them separately, and you can make images simultaneously. So that improvement in the noise that is shown in that graph, you'd like to see that. That look, I made on the same simultaneous observation taken with the old system and the new system. I made the image and I should see the difference. So these are examples of that kind. That this is a image made with the old system and this image made with the new system. And it doesn't come out very clearly, but even here you can see that this image has better clarity. You can see more details in the way this radio source. It's a radio galaxy with the central core and the jet and the lobes. I don't know if you've seen these kind of things in any of the other talks or the discussions, but you'll probably see more of them by the time the school is over. Here's an example of a pulsar observation done over 200 megahertz of bandwidth from 1260 to 1460 megahertz in the band 5, and we can now routinely do this. And you can see, so this is the pulse from the pulsar as a function of time observed over 20 minutes, and this can be done. And this is a plot which shows the improvement in the sensitivity. Again, simultaneous data taken with the old and the new system. This is the new system, so you can see the pulse more clearly with less noise, and here the pulse is looks weaker and the noise is a bit more. So that's exactly the difference in the sensitivity between the old system and the new system while using the same number of antennas for the same duration of time. Simply because of the larger bandwidth. Right? Okay, and this is an example for the third kind of science, spectral lines. As we mentioned, that you can see a spectral line either in emission or in absorption. You understand that difference? No? Okay. So when the source is emitting, then you will actually, so it's like this. So when the light bulb is emitting, you see it in emission, right? If I put a small black patch in front of it, then you will see it in absorption, in the sense that there is no signal over there, and around it you will see signal. But here, what at it and around it is in frequency space. So if there is a background source and there is a, say, galaxy or some cloud which is absorbing the radiation coming from the background source, then when you look at that source, you will find that most of the time there is some emission, but at some frequency there is a dip in the emission, and that frequency corresponds to the resonance frequency of some atomic or molecular species sitting in this foreground object, which is absorbing that radiation because it is causing the transition from the low energy to the higher energy. Okay, and so this is what is called an absorption line, and you can clearly see it, and you can see it at frequencies which it was not possible to do with the older GMRT system. So all of these are the new improvements and capabilities. Here are some more examples of spectral lines at the other bands of GMRT which are now possible. And all of these are part of the early testing, few antennas, small duration of observations, and all this will become much better as you go to much more antennas and deeper integrations, and electronics is deeper problem. So this is an example, interesting aside. So you think that you can use such facilities only for studying objects in the universe, faraway objects, but it's interesting that you can also use these for other purposes. And one of the things which radio astronomy facilities have been used sometimes is to track man-made space missions. And so you would have heard that Voyager went so far away, but you know, it is sending signals. Somebody is picking up those signals. Normally it is dedicated Earth stations that the various space agencies will build to pick up those radio signals so that you can get back the information from where the spacecraft is and so on. Sometimes these things are tricky, and you would have heard about spacecraft getting lost and then the signal is not being picked up, and then they look for something more sensitive. Can I still pick up the signal, and so on. And so there was a situation here where we were approached by NASA to work with them to build a system using the sensitivity of GMRT as the main motivation, which could receive the faint signals from the probes going to Mars. Right? So you know there is a rover on Mars which is built by NASA and sent there, and there are other such missions planned which will actually send modules which will descend to the planet's surface and explore. And there were two such. One was the European ExoMars mission, which went 2 years ago, reached Mars last year, and it had this. There's a orbiter going around the planet, and it would send out a small module which would descend and try to land onto the planet's surface. And that journey, from the time it enters the atmosphere of Mars to the time it's supposed to reach the surface, about 8 minutes. Okay, where it is fighting the gravity of the planet to make a safe descent, just like a parachute you do when you jump out from a plane with a parachute. Okay, and so and this is the most critical part of the phase of that mission, because that is when the module can get lost or destroyed if, you know, there are all calculations done that this is what will happen, this is the speed it will reach at this stage, this is the way the parachute should be deployed, this is the way the thrusters should be deployed to slow it down and make a safe landing. But they're not sure how well it will work. And so this thing emits a small radio beacon as a signal, which you can pick up and monitor its health. Is it alive? Is it working? And so on. So we were asked that can we develop a system which will pick up this signal and track it as this spacecraft made the descent. So we work with NASA. Our hardware and our systems are combined with software they develop for picking up and decoding the signal. So you can see a weak red pulse here. That's actually the signal, and the signal was then relayed live to the control room in Germany, where this ExoMars was a European mission which went there, and it was relayed live to their control room to see what's happening during this. And initially we did a test run. Well before it reaches there, it switches on the beacon as a test. Can you detect it? But before that, we tested it with the rovers. The rovers, which are already there on surface, have a similar beacon. And so there was time when it is turning on that beacon to talk back to Earth, and we were receiving, and we could detect that signal. And so this is a view from the Martian surface. You go on the rover, this is what you would see at the Earth. But we could actually detect this signal. So this is equivalent to taking your mobile phone and putting it on Mars and asking, can I pick up that signal? It's a signal of the order of a 1 watt signal being transmitted. And but the antennas are so sensitive that you can actually pick it up. And so then when the actual event happened, we were to track this during those 8 minutes and report whether it made a healthy landing or not. And so this is what happened. So as it moves, its velocity is changing, as you can imagine. So the Doppler shift of that line is changing. So the whole idea is to keep picking up the line, measure how the frequency of the line is changing, calculate the Doppler shift, and see if it is matching with the model of what should happen to the probe as it goes through the Martian atmosphere. And so this is what happened. So you can see the signal detected by Giamatti when it started at this time, and at 10:45 you can see that the signal was lost, and its touchdown time was just about 40 seconds after that it was supposed to touch down. And so till then everything was going fine, and at this point when the signal was lost, they realized that something has gone wrong with the mission. And I don't know if any of you followed the mission, which was last year in September. So it actually crashed on the Martian surface because there was some error in their calculation about what would happen to it, and so their schedule for deployment of the parachutes and the thrusters was a bit off, and so the thrusters were deployed for too short a duration, and it thought that it had reached close enough to the Martian surface with slow enough velocity that it could then land. Those calculations went wrong, and it actually, for the last 40 seconds, it was in free fall, gravitational free fall, and it ended up crashing on the Martian surface. And later they decoded all this, but this told them immediately that the mission had failed. So there was a similar request for a NASA mission, which got cancelled, which was supposed to go around the same time, which will now go, I think, next year or something, and we may still be involved in doing a similar exercise for the NASA mission, which will have the next generation of rover or something going to the Martian surface. Okay, so I showed this earlier. So this is the one that shows the events. Reaches there, releases, and it descends through this. So this was the part that we were tracking, the 8 minutes of, we call it 8 minutes through hell. So this is what it's supposed to do at the various stages, deploying parachutes, thrusters, and
touched up. See, which did not happen. Right. Okay, fine. So enough of that. And so now, what's the time? Okay. So in 5 minutes, I'll just tell you what lies ahead beyond the upgraded GMRT. So various facilities being built around the world, including our own upgraded GMRT, to keep pushing the frontiers further. But what most people are looking forward to is a square kilometer array, which is truly a next generation facility that we talked about right now. And again, to understand that, there's another sensitivity plot, but this is turned the other way around. Here, number on top means higher sensitivity, whereas in the other plot, the number was going down for lower sensitivity. And over time, now this time is from 1940 when the first radio telescope was built after Carl Jansky by Grothrieger, to the time when the GMRT was built in the 1990s, to when they hope the SKA to be ready. This is out of date. The SKA will now not be ready till 2024 or so. But the full SKA is expected to be at least 30 times more sensitive than the GMRT in terms of the capability. You say, how do you achieve that? Obviously, you need more square meters of collecting area. So that is what the thing is. GMRT's collecting area is of the order of 30,000 square meters, as we were discussing. This has a 1 million square meters of collecting area, which is what the square kilometer stands for, which is 30 times of GMRT. But so you would say, okay, fine, that means 900 dishes, right? But no, it's actually more like 3,000 dishes, because the dishes will be smaller than the 45 meters for various other technical reasons. And they will be spread out in the final array up to 3,000 kilometers compared to our 30 kilometers. So you can now imagine the resolution that array will give compared to 30 kilometer size GMRT array, and a much wider frequency range of coverage than even what GMRT has. And again, you can't build one instrument which will have that kind of coverage. So it is actually two instruments. One is the low frequency part, one is the higher frequency part. Separate design, separate technology, and also located in different parts of the world. Again, the location, so one of the big problems that we have in GMRT is the man-made interference, which I talked about, which comes from whether it's your cell phones or your TV channels or the aircraft flying over or any other man-made activity, any sparking activity. If you take your petrol-driven vehicle near the GMRT antenna, it will see the sparks which are picked up by the antenna, and so on. So you try to put these as far away as possible from man-made activity, but still within reasonable reach, so that you can go build it, maintain it, and run it, and get data from it. Okay, so the SKA has two phases. Phase 1, which is what we are currently working on, 600 million euros is the cost, and the full SKA is much beyond that in terms of this system. And like I said, that this can't be done with one kind of detector technology. So there are low frequency tiles kind of antennas with dipoles, and dishes at the higher frequencies. As you can imagine now, to transfer the data over so many antennas, receptors over such large bandwidths, the optical fiber network there will be much more data intensive. So in fact, that data transfer is more than the total internet traffic that flows on the globe today, which is a huge amount. And again, so to process that data, you need a huge amount of electronic signal processing, supercomputing capability, the best supercomputers to digest all of that data, in addition to the state-of-the-art electronics and so on. And to manage all this, very complicated software for running an observatory spread out over hundreds of kilometers and managing the large flow of data and the complex operations that it has to do. Okay, so and again, the kind of science that the SKA will do is quite significant in different areas, all the way from cosmology to galaxies to radio transients to pulsars, black holes, gravity, and including astrobiology, detecting early signs of life as well as search for extraterrestrial intelligence, all kinds of things. And whenever you in any astronomy, when you build a facility which is 5 to 10 times better than what you have today, you will always find new unexpected discoveries. That's how science goes, and what is called serendipity. Well, I never knew universe had this kind of object also, and it shows up when you have enhanced capability for detection of those things. That's how pulsars were discovered. That's how many discoveries happen in astronomy. Okay, so like I said, 2 phases. Phase 1 is about 10% of that full SKA, which is something within reach with today's technology and computing power and so on. And it will have limited coverage and lower extent, so only up to 200 kilometer baselines, but still quite large. And like I said, costing 600 million euros, located in Australia, South Africa, and this is currently in the design phase. All these slides are slightly out of date. The design phase is now coming to an end. By middle of next year, the design will be over and the construction will start from 2019 and expected to be ready for early science from 2023 and 24 kind of timeline. So this is slightly old timeline. And so this is what it is. So these are areas in these 2 places where you count number of human beings as half human being per square kilometer kind of density, which you will, unless you go to the Thar Desert, there's no other place in India where you will get that kind of human density. But there are large tracts of land which have that kind of feature, where the arrays, the core of the array will go. So think Giamatti has a central core, then there will be antennas going out to larger distances, covering good part of Australia, including some of the islands around. Similarly here, covering a good part of Africa and so on. And the project is managed with the project office, which is in UK, in Manchester. And it is, the work of the design is divided into different work packages. Like somebody is designing the antennas, some group is designing the feeds, the receivers, the optical fiber system, and somebody is designing the software for the entire observatory and so on. And there are right now 10 countries who are members of this. We joined as a full member in 2015, along with taking up an active role in some of the design work packages. It's just a timeline, it's a bit old already. And so we are an active member in the SKA, and we there are 2-3 different things. One is having a sensitive facility like the GMRT. So when you build something like the SKA, you need to know what happens in the smaller telescopes, what lessons you have learned, how well do they work, which technology works well, which one should be adopted, and so on. So there are these pathfinders and precursors for the SKA. So GMRT is identified as one of the pathfinders. And pathfinder is literally that, to help you find the path towards the building of the SKA. What did you learn by building it like this? If I want to build something like this, can I try it on your telescope to see how well this technology works, and so on. Okay. So we are providing some of that because we have a fairly good sized instrument with good capabilities. But in addition to that, we are also involved in the actual design of some of the packages of the SKA, and we are actually leading the design for the telescope manager, which is the full monitor and control system for the entire observatory from end to end. From the time when the astronomer submits that proposal that we were talking about, to how the proposal is submitted, how it is evaluated, what it is approved, how it is scheduled on the telescope, when it is scheduled, how the observation is executed, how you control the various systems when they execute the observation, when the observation is over, how you ensure that the correct data has come, how you tell the user that your data has come, how does the user take it out from there. So there's a whole complete end-to-end chain for running the observatory, which is called the telescope manager in SKA terminology, where we are the leading institution working with members from 7 other countries for the design of the telescope manager. And that design is now coming to an end. By February, March, we will be submitting the final design documents for review. And once they are reviewed and accepted, then there will be work done to how to build and execute that design. Okay, and so we are also involved in some of the other work packages at a lower level. And so this is like a quick summary of Indian participation in the SKA. Technical design, in the construction phase, and we will be involved in the design phase, and we'll be involved in the construction phase later on, and involvement in the pathfinders, both in the GMRT, and some of the other colleagues in India are involved in some of the pathfinders in other countries as members and contributors. And of course, one of the important things is preparing for science with the SKA. So when you have such a big, complicated facility, your scientists and astronomers need to know how to use it. Even like, if you were to say, well, I want to use the GMRT, you need to know what is to be done, what is required, how do you understand the instrument, how do you propose a science experiment, how do you carry it out, what kind of tools you need to analyze the data, make sense of the data. So you have to do all of that preparatory work before you can, hope to carry out an observation with the GMRT. Same applies for the SKA. It's a bigger facility with many more capabilities. So our aim has been to grow the Indian community of astronomers to be ready for that. What technology is needed as well. If you, how do you understand it? Can you do similar experiments with the GMRT to learn how these things are done, and then go on from there to the other pathfinders and work over there. All of that is going on, and all of that, of course, requires more people to be involved, or spreading the word and getting the manpower, and hopefully that includes some of you as you grow and decide your careers. And so this is from just a historical thing from the time when our government signed the document to become members of the SKA organization. So that's the chairman of DAE, Atomic Energy, which is our nodal ministry, along with the SKA Director General signing the ceremony. And so we are doing, like I said, we're doing all these various technical activities. We are also, so there's an example of what we do when we are managing this telescope manager consortium with different countries involved, doing different bits and pieces, along with partners from industry. So we are working with Tata Consulting Services, Subsystems Limited in India. Other colleagues in UK are working with some of their industries over there. So it's it's really a huge, big joint effort to build the system. Again, like I said, the telescope manager it's like the brain and the nerve center of the entire observatory. It is the one that controls everything. It talks to everybody, it gets information, it takes the decisions, what is to be done, and so on. So it's a fairly complicated piece of software and certain amount of hardware also which is needed to make this happen. I won't go into the details. And like I said, in terms of science activities, there are national science working groups for different areas of interest. So as a young student, you can join if you're interested in these areas to see what's happening in that area of science in the country. Who are the people who are working in that area? What are we talking about? What kind of experiments? What kind of theoretical studies? What kind of simulations? And so on, in order to be ready for science with the SKA. So every year we try to have an annual meeting. So this year again, at the time of the Astronomical Society of India meeting in Hyderabad in February, we will be having a one-day workshop for the SKA science. What is the developments that have happened in the last 1 year? Are we ready? And so we also hosted the International SKA Science Meeting in Goa last year in November and December. And all of this is coordinated by SKA India Consortium, which has memberships from various institutions within India who are interested in either the science or the technology associated with the SKA. And it's managed by a high-level committee set up by the government, the SKA India Steering Committee, which gives overall guidance about activities and provides funds to support the activities. Okay, alright, so we'll stop here. If you have any questions, you can do that now, or you can come and catch me anytime later on. Yes? Yes.
So that the optical fiber are becoming the transmitting losses. So there we have 3,000. So how is it?
Yeah. So first of all, that reason that you gave for why that shape is chosen is not quite the correct reason. So the reason is dictated more by which we didn't go into. So we didn't go into how this interferometry business works. How do you synthesize an aperture whose resolution is the resolution of this area by using these dishes which are spread out? We didn't go into that, but if you did go into that, I don't know if you have had any lecture, and I don't think you'll have lecture if you go into that detail. So what is important there is that somebody used the word baseline earlier. So every pair of antennas is a baseline, and you need to have enough number of these baselines. You can think of the baseline as a vector. It's a two-dimensional vector. You need to have enough vectors with different lengths and different orientations in order to really do a good job of making the image when you take the data from all of these baselines and do the signal processing. So you can ask so it's an optimization problem. Supposing I had n antennas and I ask how should I arrange them such that I get all these, the NC2 combinations that I get will give me the maximum number of vectors spread out on the 2D plane. Okay, and so when you think about that problem, you find that one of the optimal configurations for doing that is a Y-shaped configuration. There are other possible, like you saw in the SKA thing, it was more like a spiral of antennas going out. So a spiral is another configuration. So there are a few configurations which are more optimally suited. But given n antennas, how to place them so that you get the maximum number of non-redundant baselines, unique baselines coverage. So that is what drives the configuration. Once you've decided that, then you have to build the optical fiber system which will not give you too much loss. So you can keep the loss under control and still get good quality signal coming back. Now tell me, what is your question? Yeah, so that is what is actually done. Then you match your optical fiber system to meet this requirement. Okay, what else? Anybody else? Okay, so then you all should go off, have lunch. What time is your next lecture, or do you have tutorials or something in the afternoon? Experiments.